To more GCSE physics, going through topic by topic. We're going to look at more about radiation today. We're going to have a look at some more in-depth look at some of the bits and pieces. In the last time I talked to you, we had a look at radiation experiments that were done by Lord Ernest Rutherford and Marsden and Geiger. I want to have a look at a demo of this experiment. So let's go over and have a look at this. Now what I've got here is a representation here of an atom. Yeah, it's not a very good one, I have to admit, that it's simply a piece of plastic which is raised here, and this represents the nucleus. And what I'm going to do is I'm going to fire one of these. It looks like an alpha particle here, or like marble, but we're going to try and fire this marble at this atom. And we fire this, and for most of them they go straight through. In fact, if I do this lots of times at different distances, moving all the way across, then for most of them they just go straight through and collide at the other side. Normally when I do this experiment I hide this section from the students so they can't see what's going on, but for you I've done this specially. I've not put that in there because we're not in the process of trying to guess what we've got. Now if an alpha particle comes near to the nucleus, then I didn't give it enough welly, because alpha particles have a fair bit of welly, they are being deflected rather than going straight through, hitting where they're being launched. We're getting some sort of deflection, and we can see this deflection and work out that something is going on. Very occasionally we hit this straight on, and it shouldn't go over the top too much welly, and we're getting then massive deflections. And if I can do it right, we can bounce them almost back in the direction we came from. And if I could actually get this a little bit steeper perhaps, then most of them will, 99% of them or more, would go straight through, and only the smallest amount will go up and be reflected back. So this gives us an idea of what the nucleus must look like, that we've got this field here of positiveness, and when the positive particle here of an alpha particle comes nearby, then it will be deflected. So there we are, a way of looking at this alpha particle scattering experiment done by Lord Ernest Rutherford and his two students Geiger and Marsden. At a experiment, we've looked at a little bit about some of these radiation, these things. Let's have a look at this in perhaps a little bit more detail, and we'll have a look at something about their penetrating power. So we'll start here with our radioactive particles. I know gamma is technically a ray, and we're looking at the penetration So we've got our alpha particle, and what can this try to penetrate? Well, it's stopped by basically a piece of paper, and what we can do is we can find that it's got a range of about 10 centimeters in air, probably less than that. And so these particles, although big, are perhaps not as dangerous. But wherever we go, we find there is a lot of these particles around. Beta particles can get through probably up to about 3 millimeters of aluminium and travel perhaps up to a meter or so in the air, perhaps even more. Depends upon their power. And then the gamma rays, these are much harder to stop, and we're looking at probably a fair bit of concrete or lead to try and stop these, and they're going to travel, I'm just going to put down here, a long way, because basically we're not going to manage to measure those. The penetration power of the gamma rays can be quite considerable. So here, these will spread out in air. We can get through lead, probably it needs sort of, I don't know, several centimeters of lead. Let's say 5 to 10 centimeters of lead would stop it. Maybe concrete is about 1 meter or so. So we've got a difference in scale of the power. The range in air here, people argue about these numbers. I would say here it's not going to be greater than 10 centimeters. And this one again is only about 1 meter. We have to think of this when we come to think about the radioactivity dangers. There are two basic dangers we look at. They are contamination and irradiation. Contamination is where you actually bring the stuff with you. It gets attached to you, either inside or outside. So we have basically here our radioactive material literally touching with you. Irradiation, on the other hand, is where we have a source of radiation coming out, and you might pass through that sort of beam of radiation. Once you've passed through it, you're no longer susceptible to it, and we meet this basically all the time, and it's very hard to try and get around this problem of irradiation, because this is all about us, and that we call background radiation. So when we do an experiment, what we normally do is we basically test the background. Once we've got the background radiation, that's going to give us some sort of count for background. Then we test our object, and we have our object count, and we take away the background, and that will give us an estimate. Remember, radiation is a random occurrence. both the object and the background. Background radiation causes us considerable amount of problems because it is all around us in where we go and what we do. Let's have a picture of this. We've got here where the radiation comes from, and most of this is in the air. So a good sort of 50% of all our radiation is in the air that we breathe. We get some from the ground. And where's this? Well, this is in literally the ground we walk on. The rocks, some of them are radioactive. They decay and give out radiation. Our next common source is the cosmic rays. These coming from not just the sun, but all the stars that we can see, and perhaps some that we can't see. And we can see that this makes up about 3/4 of all the radiation that we are exposed to. The air, the ground, and direct radiation from the stars. Don't be fooled, in the daytime the stars are still there, you just can't see them. Their radiation's still coming through. Some of the radiation is picked up in plants. Those plants transfer it to animals, and we eat the plants, we eat the animals. So in the food that we eat, and it doesn't matter if you want to be vegan or vegetarian, you're still going to bring in about that amount of radiation. We pick up some with medical. This is all the different sort of treatments we might have with radioactive tracers, where we might put in a radioactive tracer to somebody to find out where there's a problem. This person here might have a problem. Let's suppose we have our person. I'll draw us a really nice person here, and what they've got is they've got an organ which is blocked. What we do is we put in radiation, and it can't go past a certain bit, and we can see a build-up. Therefore we can work out where the blockage is. Personally, I feel this person is in serious need of surgery, just to make them look perhaps a little bit more human. So we've got medical. This is not just radioactive tracers, but it's also going to be looking at things like X-rays and trying to sort out cancer. And then we're not left with much else. We've got some air travel. The higher you travel in an aircraft, the more likely you are to be exposed to some of these cosmic rays. And that's only less than 1%. And then we get some others from fallout from Fukushima, from Chernobyl, from various other places, other bombs that went off many years ago. Some of that radiation is still with us. And lastly, we've got to dispose of the waste from a nuclear reactor, and we've got to store it somewhere, and various other occupational uses. And you can see it makes up a tiny fraction of where you get your radiation from. So we have to consider this as being a bit of a problem, but then not really such a problem. So we've got radiation in sort of medicine, trying to use that to try and help us. We've got our radiotherapy, where we literally try and kill a tumour and hopefully not try to kill the host. And that we do this way. Let's suppose I take a cross section through a human body and we're going to give this person a nice tumour. And what we can do for this person is we can bombard them with radiation. So I can take a radioactive source and I can aim it through this person. I can move that source and I can then aim it again through that person. And I can move it again and I can aim it through that person. And now we've got a situation where all of these tissues are exposed to one dose of radiation, but the bit that we're aiming for will receive 3 doses of radiation, and maybe that will be enough to kill that but not harm anything else. It's a little bit of a gamble, really. So we've got 2 uses of radiation in medicine. We've got it as a tracer and we've got it basically for identifying where there's a blockage, or occasionally sort of looking at sort of how an organ is actually working. We've got several ideas here. The problem is if you inject a tracer into the person, they are going to become radioactive. So we'd want to make their half-life of these things fairly low. And if you don't know what half-life is, stay tuned because we're about to go through that one. Now we can also choose what radiation we're going to emit, alpha, beta or gamma. Alpha at close range is going to do a lot of damage, so probably not that one. And beta radiation is going to cause us perhaps some problems, so gamma might be the best choice because it's going to do perhaps the least damage to the person. We can also use gamma cameras. And simply a gamma camera, you'll be given this tracer and we can use this to try and take a picture of that bit of the person. It'll only record where the radioactive substance is. So we've also got this here in therapy, as I've described there, to try and get rid of it, and occasionally we can use radioactive implants either at the microscopic or the macroscopic level. Microscopic, we might be able to get this into certain antibodies, so they literally target one cell, or we might put in a slightly larger bit into a tumour to try and kill it off. You want the half-life to be long enough that it's going to damage the item you're trying to kill, but not too long so that it actually damages the person. Radiation's dangerous, and I can't stress that one enough. We can use it in business. We can use it to perhaps measure the thickness of metals. One of these is the production of aluminium, and when we make aluminium we pass beta rays, beta particles through the aluminium, and we know how much it's going to take to absorb it. if the rollers are too far apart and the aluminium then is getting too thick, then more radiation is going to be absorbed, and we can measure that, and we know therefore it's too thick, so we can push the rollers close together to make the aluminium foil thinner. If it's too thin, then the radiation number goes up, so we then need to make the rollers further apart, and by adjusting this continually we can make thin aluminium sheets. So radiation can be quite useful. There are many places we can try and use this, and none more so than the smoke alarm. So let's have a quick look at a smoke alarm. The other one. And let's have a look at this one. So my son's just handed me the smoke alarm that we've taken off from the ceiling, and here is my smoke alarm. Here we've got a radioactive source, an alpha source, passing radiation out across a small distance, and while it's doing that it makes an electric current. All is well. When the smoke gets into this, then what happens is that the smoke stops the radiation going across, and it sets off our alarm. And that warns me we've got a problem. And I'll pass that back to my son so he can put it back up, and I can feel a little bit more protected by having a smoke alarm there ready to help me. Now, my next little topic to have a look at is that of looking at half-life. Now, I've done a couple of videos on this, so I'm not going to do that. I put a link in the description to my half-life experiments where you can have a look. But basically, I'll just quickly show you what this is, and what we have are a couple of ways of doing this. And I've got a box of counters, and these are two-sided counters. They represent my nuclei. We drop them, and then what we do is we can see that because they're half one colour and half the other, then I can remove one half and we can count up the other. And you can see that if we do this experiment, then we can get some interesting results. I start off with all my and they're all orange to start with. We then shake them up, tip them out, and the colour, half of them you can see are yellow and half are red, and then I could perhaps chuck away all the yellow ones. They are a material. We've changed this red substance into yellow. I've changed perhaps my potassium into calcium, and then we wait another period of time and we look at that again, and we can see that half of the nuclei have decayed into something else and half left, and we can see that this follows a curve, a half-life curve. Now, every time I do this I get different results. Every time I do this it's the same shape. It doesn't matter if the lines go up or down a little bit. It always gives me this particular half-life curve. My half-life curve looks, press the wrong button, something like this one. The half-life curve will look something like that. And let's say my count here is 400, halfway then 200, halfway 100, halfway 50, halfway 25. So let's suppose to start with I'm at 400. This on the bottom here is time. I'll push that across for you a little bit better so you can see it. Here we've got 200, and we can measure the time here taken for half the amount to decay. We get to 100 and we measure this one, and we find that this distance is the same as that distance, the time for half to decay. And we look at 50, and that distance is the same. It's the time taken for half to decay. In my graph it's only approximately right because I've only just drawn a vague curve here, but the time taken for half the amount to decay is called the half-life, and different substances take a different amount of time to decay. Some of them will decay really quickly, so we're going to have some in the order of seconds, to some which are going to be the order of billions of years. If something's decaying very quickly, it's going to give out a lot of radiation quickly. Something that's decaying very slowly is going to take a long time to get rid of its radioactivity. So this one is marginally safer than that one, but I wouldn't like to put and bank my life on this. So half-life is important. It's a random decay of particles from one substance. So let's have here potassium. I was just trying to think of the numbers of potassium here. So that's going to be about 19, isn't it, for potassium, and it's got an atomic mass of 40. This will give out a beta particle. One of the nuclei, one of the neutrons will change to a proton and give out a high-speed electron, and we've got one more proton. This means that we no longer have potassium, but instead we have calcium. This is what's happening here. We're getting our red potassium turns into, or at least half of it turns into, the yellow represented here, calcium. So this is our way of trying to look at half-life, the time taken for half the substance to break down. Let's have a look at a calculation doing this. So if we're going to have a look at half-life, I may have so much substance. So let's suppose I've got 64 counts from my material, and I'm told it's got a half-life here of 30 minutes. So in 30 minutes it means that half-life should be down to 30 counts. By the time it's dropped to 16, half of that 32, we've gone through 2 half-lives. By the time it's dropped down to 8, we've gone down here 3 half-lives. By the time it's dropped to 4, then we've got 4 half-lives, down to 2, 5 half-lives, 1, 6 half-lives. So 30 minutes, 1 hour, 1.5 hours, 2 hours, 2.5 hours, 3 hours. And once we got down to 1 count, then it's random. The next one could be, of course, 1 or 0. In reality, we wouldn't get these numbers. Maybe this might be 65, this might be 28, this might be 18. But if we repeat these experiments enough times, then these are the numbers that we will see. And we will see this number drop by half every, for example, in this imaginary case, every 30 minutes. So this is half-life. We've got our random decay of material, and it breaks down literally randomly, turning one substance into another. So that's activity, that's medicine. Let's go on and have a look at something a little bit more useful in radiation. We'll have a look at what we could use this productively. And what I've got here is a little picture for you to have a look at. This is a diagram of a fission reactor. A fission reactor, this one made by the Encyclopedia Britannica. It's one of the best pictures that I've seen. So hopefully there's a nice little plug for Encyclopedia Britannica. Go and have a look at it on their website and you can see their picture of a fission reactor. Let's have a look at it. Here is our reactor. Now I'm going to improve on their picture. I use the word improve very loosely, and what I've got here is my nuclear reactor, and into this nuclear reactor we're going to put some fuel rods. Now these are typically going to be made of uranium, and so what I do is I push some of these rods into this nuclear block. Now this works by taking a high-speed neutron, and this neutron smashes into a piece of uranium. And if it's the right sort of uranium, then the uranium atom will be split in two, and it will form two new elements, in this case krypton barium, and it's going to give out 3 high-speed neutrons. Now if these neutrons are in very close proximity to more uranium, then what we're going to do is we're going to get more of these reactions with more heat being given out. So this doesn't go critical. What we do is we need to put in a moderator. So in here we're going to put in some water, and this water acts as a moderator. It slows down these high-speed neutrons, and as it slows these high-speed neutrons down, then we have less nuclear reactions. So we also can stop the reactor here by putting in other rods. And these are control rods. And they're often made of boron or some other materials, and if we wind these in, they're going to absorb all the neutrons that come out, and they're going to make the reactor a lot safer. The biggest problem that we have with all this radiation is that if you've got more than a critical mass of uranium, then that's going to give us a problem. While we've got a small amount of uranium, it's not a problem. We get to a critical mass, then it's not going to matter whether you've got these rods in or not. We're going to get a runaway nuclear reactor. And the problem is with that after a little while we get a nuclear meltdown, or worse still, a nuclear explosion. So let's look at what's going on here. We've got a pressure vessel and we pump in water into this reactor. The water flows through, and as it does so, these rods, these uranium rods, are hot. They're giving out heat, so the water gets very hot, and that passes out and is cooled by some more water in another tank going through. This tap water, as it goes through, gets very hot. It's turned to steam, and this steam drives a turbine. That water, as steam, has now been turned to water, and it's condensed here by cooling it, and then it runs back into this pump. Now this water should not become radioactive, although it is slightly exposed to some radiation here. The steam, as it drives the turbine round, drives an electric generator. The generator then produces electricity, which goes off down some transmission lines. This water needs to be cooled, so this water we take in from a lake, a river, or perhaps even the sea. We put this in the bottom of a cooling tower, and then this water goes into a condenser here, and that's cooling this water that's going into the reactor down, and that water here is then sprayed onto, well, it's just sprayed really in this little chimney to allow it to basically cool down, and then it can be pumped round again and again and again, and we get some non-radioactive water vapour evaporating. So at some nuclear reactors we see this water vapour going off, but it's not radioactive. It's just being used to cool the water down. Now in some places we can use this cooling down to try and perhaps heat some houses during the winter. So a nuclear fission reactor is really a very efficient system. We can take nuclear material and lots of it, most of it, is converted into energy, much more so than we would get with other types of fuels such as fossil fuels. They're not as efficient. So nuclear is great. The only problem is what are we going to do with this waste? Once these uranium rods are spent, all the energy is being taken that we can out of them, all the useful energy, then this becomes nuclear waste which we need to store. Only certain uranium atoms work. I mentioned here I've got uranium here 235. Generally in the world only about sort of uranium, here we are, 235, I don't know, 1 to 3% of all the uranium would be that. It's gradually getting harder to find. So mostly what we actually find is uranium 238. So what we need to do with this, because it won't undergo fission, we can change this into plutonium 239. Once I've got this made into this, then we can actually create this in a plutonium reactor. We can also use it to make various other things. So a fission reactor, very useful, but it can only use certain fuels, and if we get the fuel too concentrated, or we have it too close together, or we don't have enough control rods in there, then it can undergo a chain reaction, and we've got really there a big problem. So the other type of reactor is one called a fusion reactor. Now, I live in the south of England, not far from London, and a question is, where is my nearest nuclear fusion reactor? And I'm going to be a bit more specific. Let's have a working one, because someone that says they've got a non-working fusion reactor, it's like saying that, you know, I've got a model car, you know, it's a Ferrari, and everyone thinks, yes, you've got a Ferrari and you can drive around it. No, you haven't. So where is the nearest working fusion reactor to where I live in Hemel Hempstead in England? And the answer is about the same distance everywhere. It's the sun. Yeah, those stars that shine in the sky, they are fusion reactors. What they do is they take some hydrogen atoms, and sometimes we might take heavy hydrogen atoms, and what we do is we fire them next to one another very closely. In the sun, this is done by immense pressure, this gravitational force pulling these atoms together, and what happens is we make helium, plus we get given out an awful lot of energy. Now, this doesn't make any radioactive material, so this looks like this is really useful. So we can take some hydrogen, some heavy hydrogen called deuterium, and we can make lots of helium gas, which we could use for all sorts of things. The helium is not dangerous, it's not radioactive, and this would be wonderful. The only problem is, at the moment, most of these reactors take an awful lot of energy to get them going. They've got to squash this hydrogen together, so immense pressure. We've got to increase the heat, so immense heat. That costs a lot of energy to do that. And they get out, yeah, a little bit. And for not very long, like a few seconds, and then it all shuts down. we haven't managed to get a working fusion reactor yet. Now that doesn't mean to say we won't get one. It just means at the moment we haven't got a working one yet. And people are working, the best minds on science are working on trying to get this to work. And if it does, then we can make all the right sort of energy that we need. It will be non-radioactive, and we will have, in theory, cheap, free, perhaps, electricity. And do bear in mind nothing's actually ever free, because it costs a lot of money to build these reactors. So a fusion reactor looks like it will be the future for us, but not yet. So it's got a promising future if we can get round the various problems trying to sort it out. Finally, we look at what are the nuclear issues today. Fukushima, Chernobyl, 2 nuclear fission reactors that for one reason or another went wrong. And there's a very good documentary on Chernobyl that you can watch. We've got the nuclear waste. What are we going to do with that? We put it in old mines. Yeah, and it stays there. How long for? Well, thousands of years, and it's got to be maintained for thousands of years. Well, that's not necessarily nice for your descendants. I don't even know back a few generations who my family were. I can only track them back, some of them, to about sort of 1600, some even less than that. And we're expecting perhaps children, our children, in the year 3000 or more, still to be looking after our nuclear waste. We're building new nuclear reactors, but the energy, the fuel to make this, we're running out. We're using uranium. We're running out of uranium. What can we use instead? There are some others. Thorium reactors are postulated, and there's a lot more thorium around, so maybe that might be an answer. Our problems are half-life. How long do these things stay around? How long are we going to have to get our children's children and so on to look after our nuclear waste? When we started this, I said there's a problem with nuclear material. The problem with nuclear material is this item here is radioactive. But I can't see, I can't smell, I can't taste, I can't touch the radiation, but it's there. This is just a plastic lid, but it still is very slightly radioactive, and so are you. So big problems with this. If you want to have a look at more on nuclear issues, there are some very good YouTube videos out there on perhaps the most radioactive places on Earth. A very good one by Veritasium. There are lots to have a look at, and it's useful to know. So radiation, very dangerous. If you liked what you heard and saw today, then please like this and subscribe, and hopefully then you can learn more GCSE physics topic by topic, and I'll see you next week when we'll have a look at some more physics. Until then, stay safe. Bye bye.